Right now, the building you are sitting in is actively trying to crush itself.
Yeah, that's entirely accurate.
Or, freeze you. Or suffocate you in a sealed glass box.
Right, the environment is relentless.
Yeah, the external environment is just pushing against the walls, right? The moisture in the air is trying to rot the foundation. And the heat generated by the electronics around you is basically trying to cook the room.
And the only reason it isn't succeeding is this highly orchestrated, totally invisible operating system.
Exactly. It's this engineering landscape that we completely take for granted. Well, until it fails, anyway.
Yeah, it's kind of the ultimate paradox of modern architecture, right?
That's for sure.
Like, we obsess over the visible stuff, the sweeping curves, the glass facades, the structural steel holding the whole thing up.
The shiny things.
Right.
Yeah.
But that structural shell is essentially just a very expensive cave.
Wow, an expensive cave. I like that.
Yeah. What actually makes it habitable, what manages the air you breathe, and the thermal dynamics keeping you alive, all of that is entirely hidden in the walls and ceilings.
And that is exactly our mission for this deep dive today. We are exploring that invisible operating system.
It's a massive topic.
It really is. We are going to unpack a set of documents that literally dictate how our world is constructed. I mean, we are looking at the ASHRAE Handbook.
Which is quite the read.
Oh man, the sources we've pulled together for this are intense. We've got the official historical overviews, the incredibly dense table of contents for their most recent volumes, and some really deep-cut technical analyses of building systems integration.
It reveals something wild, doesn't it?
It really does. We're going to look at what these massive volumes actually do, right? And how a global network of practicing engineers keeps them updated.
Right.
And how, like, a microscopic rule change about a single pipe fitting can completely alter the architectural blueprint of a hospital on the other side of the planet.
If we connect this to the bigger picture, the scale of its influence is just hard to overstate.
Yeah.
Yeah, I mean, when you realize that the vast majority of human beings in industrialized nations spend over 90% of their lives indoors.
90%? That is wild.
It is. You start to understand that our comfort, our safety, and our long-term health are entirely dependent on the principles codified in these very specific texts.
Okay, let's unpack this right from the jump.
Let's do it.
Because if I want to understand how a modern building survives an extreme climate or, mitigates an airborne virus or handles the massive localized heat of a new AI data center.
Which is a huge issue right now.
Right. I need to know what tools the engineers are using to build it. And the central tool is the ASHRAE Handbook.
A foundational tool, yes.
But looking at our sources, calling this a handbook is almost comical.
Oh, yeah.
It's not like a quick reference guide you keep in your glove box. It is a massive 4-volume ecosystem.
Yeah, handbook is definitely a legacy term that underplays what it actually is.
Very much so.
Because the scope of the built environment is just far too complex for a single text.
Right.
So ASHRE, which stands for the American Society of Heating, Refrigerating, and Air Conditioning Engineers, by the way, though they operate globally now.
Got it.
They divide the foundational knowledge into 4 distinct volumes. And they are structured really logically, starting with the absolute bedrock of physics in the fundamentals volume.
Right, because before you can, buy a fan or design a duct, you need the raw math.
Precisely. You have to have the math. Fundamentals covers thermodynamics, fluid dynamics, and psychrometrics.
Psychrometric.
Yeah, it's the study of the thermodynamic properties of moist air.
Oh, interesting.
Which is critical because humidity control is arguably way harder than temperature control.
I would have never thought about that, but that makes sense.
And it also contains the exhaustive outdoor climatic data.
Yeah.
You just can't calculate the thermal load of a building if you don't have the historical extreme weather data for the specific latitude and longitude where you are building it.
Okay, so you start with the physics and the weather in Volume 1.
Right.
Then you move into the hardware, I'm guessing. Looking at the breakdown, that seems to be split between 2 volumes. Refrigeration and HVAC systems and equipment.
That's a really good way to look at it. The refrigeration volume dives deep into the hardcore science of low-temperature applications.
So not my kitchen fridge.
No, we aren't talking about residential refrigerators at all.
Okay.
This is industrial food preservation on a massive scale, cryogenic freezing, and heavy industrial process cooling.
Wow. Okay.
Then the systems and equipment volume is your physical hardware directory.
Right, the actual machines.
Exactly. Once you know your thermal load from the fundamentals volume, this is where you go to understand the performance specs of the actual machines. chillers, boilers, pumps.
Massive centrifugal fans.
Right. And the distribution networks of pipes and ducts. It's the physical gear.
Which brings us to the fourth volume, and honestly, this is the one that makes the whole system click into place for me.
The applications volume.
Yes, HVAC applications. This is the synthesis, right?
It is.
It's how you take the raw physics from Volume 1, the cold storage science from Volume 2, and the massive hardware from Volume 3, and actually combine them to build a specific functional reality.
It's the crucial final step. Because having the most efficient boiler or the most powerful air handler means absolutely nothing on its own.
Right, it's just a machine sitting there.
Exactly.
Yeah.
It means nothing if you don't know the specific, highly regulated environmental requirements of, say, a neonatal intensive care unit versus a commercial bakery.
Oh, wow. Yeah, those are two very different environments. I was thinking about this while reading through the volume breakdown, and it totally maps onto the culinary world.
Oh, really? How so?
Well, it's like fundamentals is the underlying chemistry of cooking.
Okay, yeah.
Like how heat transfer denatures a protein or the Maillard reaction.
Sure.
Then equipment is your physical kitchen appliances, your high BTU ranges and immersion blenders.
Right.
Refrigeration is the food safety and cold chain logistics. And applications is your highly specialized recipe book.
That is a fantastic analogy.
Because they all use the same heat and cold, but the blueprint for running a high-volume diner is fundamentally different from a sterile Michelin star sushi prep room.
That is an excellent framing because it really highlights the systemic reliance between the texts.
Right.
An engineer, or a chef in your analogy, cannot successfully execute an applications design for a 100-story skyscraper without continuously pulling exact mathematical constraints from the other 3 volumes.
They have to talk to each other.
They do not operate in isolation at all.
But that interreliance brings up a massive logistical hurdle, I think.
What's that?
Well, if this is a static recipe book for the entire physical world, it would become a death trap within a decade, right?
Oh, easily.
Because technology shifts, climate zones are actively changing, and the density of how we use buildings is constantly evolving.
Oh, true.
So how on earth does a global standard stay ahead of the curve without, paralyzing the construction industry with outdated codes?
Well, they handle it through this relentless, staggered update mechanism. It is a strict 4-year rotating cycle.
Okay.
The entire handbook isn't published all at once and then left to age. Every single year, one of the 4 volumes is completely torn down, revised, and published anew.
Meaning no single volume is ever older than 4 years.
Precisely.
Our sources note that Fundamentals is scheduled for a 2025 release, Refrigeration for 2026, Equipment just updated in 2024, and Applications in 2023.
Right. It's a perpetual engine of technical consensus. And the digital transition to ASHRAE Handbook Online has accelerated this even further.
Because they can just update it live.
Exactly. They don't even have to wait for the print cycle anymore to issue critical updates.
Oh, wow.
If a major technological shift happens, say a breakthrough in variable refrigerant flow systems, they can push out-of-cycle technical developments digitally.
That makes sense.
Complete with integrated calculation spreadsheets right in the text.
Okay, but I have a serious logistical hang-up here.
Okay, lay it on me.
I was reading the structural breakdown of who actually writes this stuff.
Uh-huh.
It says, this global standard, the rules that govern the safety of nuclear facilities, level 4 biolabs, and high-rise structures, is run by a decentralized network of volunteers.
That is correct.
You're telling me the invisible operating system of the modern world is essentially an open-source weekend project?
Well, I wouldn't call it a weekend project, but yes, the core engine relies on volunteer labor from thousands of professionals.
That seems incredibly risky, doesn't it?
It sounds like it at first.
Like, what is stopping a massive HVAC manufacturer from stacking a volunteer committee and writing the rules so that only their specific proprietary equipment meets the new code?
Right.
How do you prevent corporate bias from literally writing the laws of building physics?
That is the exact friction that makes the system robust, surprisingly.
Wait, really?
Yeah, you are totally right to point out the risk of commercial bias, but HVAC mitigates this through a remarkably strict governance structure.
Okay.
The volunteers aren't just anyone walking off the street. They are organized into highly specific technical committees, task groups, and multidisciplinary task groups.
So they're experts.
Oh, absolutely. You have one committee entirely dedicated to tall buildings, another strictly for kitchen ventilation.
So they are deeply siloed experts.
Deeply.
Yeah.
And to prevent that corporate capture you mentioned, the Handbook Committee, the HBC, enforces strict balancing rules on these committees.
What kind of rules?
Well, you cannot have a committee made up entirely of manufacturers, for instance.
Oh, I see.
It must be a balanced matrix of consulting engineers who design the systems, academics who study the physics, building owners who pay the energy bills, and, yes, competing manufacturers.
So you put the rival manufacturers in the same room with the academics who have no financial stake and force them to agree?
Exactly. And the authoring protocols are brutal. A chapter cannot simply be submitted by one guy.
It has to go through a process.
It requires a recorded vote of approval from the active technical committee members.
Right.
When an engineer casts a recorded vote on a standard that will govern hospital ventilation, their professional license, their reputation, and immense legal liability are tied to that consensus.
Okay, that shifts the perspective a lot. It's less hobbyist and more like ground truth peer review.
That's a great way to put it.
Because if you just paid a dozen theoretical physicists to write the standard in a vacuum, they might design a mathematically perfect boiler system that is, physically impossible to install in a cramped real-world basement.
Which is exactly why the practitioner model works so well.
Yeah.
The people arguing over the codes are the ones who actually have to swing the wrenches and defend the designs to building inspectors.
And this leads us to the most fascinating part of the technical analysis in our sources, the ripple effect.
Yes. The
Yeah.
dependencies.
Because the volumes are updated on this staggered 4-year cycle, a change in one volume doesn't just sit there. It triggers a massive design shift in the subsequent volumes.
It forces a constant rolling evolution across all the engineering disciplines.
The sources give a really clear example of this regarding pathogen control. Look at the last few years. Airborne viruses are obviously top of mind for everyone.
Without a doubt.
In the 2024 Systems and Equipment volume, the committee heavily updated the guidelines on germicidal UVC lamps and humidifiers to combat aerosol transmission.
The highly specific hardware update, right?
Yeah.
They are dictating the exact wavelength of light required to disrupt the RNA of a pathogen as it moves through a high-velocity airstream.
Which sounds like sci-fi.
It does. And they have to figure out how to do that without accidentally generating harmful ozone in the ductwork.
Right. But that hardware update in the 2024 volume immediately dictates how the 2023 Applications volume handles the physical layout of real spaces.
Yes, the ripple effect.
Because the lamp specifications changed, the way you physically design the ceiling layout of a third-grade classroom or a dental clinic has to change to accommodate the new equipment parameters.
It completely eliminates siloed thinking.
Right.
A brilliant, highly lethal UVC lamp is useless, or worse, an actual radiation hazard, if the engineer designing an elementary school doesn't have a codified, safe way to integrate it into the room's specific airflow patterns.
Here is another wild example from the sources that just blew my mind. The shift to flammable refrigerants.
Oh boy, yeah. That's a big one.
The industry is moving away from coolants that have a high global warming potential, or GWP.
Right, which is a good thing for the environment.
Absolutely.
Yeah.
But the catch is, the new low GWP alternatives they're adding to the equipment volume are classified as A2L, which means they are mildly flammable.
Yes, and if we connect this to the bigger picture, that is a massive paradigm shift.
It sounds terrifying.
Well, for decades, the industry relied on non-flammable refrigerants, but they were terrible for the atmosphere. They trapped heat.
Right.
The chemical trade-off for a molecule that breaks down quickly in the atmosphere, meaning it has a low global warming potential, is that it tends to be less stable and therefore slightly flammable.
So to save the ozone and reduce warming, we basically have to pump flammable gas through the walls of our buildings.
That is the complex physical reality we are dealing with right now.
And here is the ripple effect. Because the equipment volume changed the chemical nature of the coolant, the applications volume had to rewrite the structural blueprints for mechanical rooms.
Entirely.
Especially in massive data centers. If a pipe leaks now, it's not just an environmental issue, it's an actual combustion hazard.
Exactly. You are no longer just designing a room to hold a chiller.
What else do you need?
You are designing a room that requires active leak detection sensors, automated purge ventilation systems to instantly exhaust the gas.
Wow.
And in some extreme industrial cases, blast-resistant construction.
A chemical tweak in Volume 3 literally adds reinforced concrete and specialized exhaust shafts to the architectural blueprint in Volume 4. That's incredible. It's all deeply connected.
Let's look at one more mechanical example from the sources before we dive fully into the specific building applications. Water hammer.
Oh, water hammer, yes.
I'll be honest, I've been in older industrial buildings or even big apartment complexes where the pipes suddenly sound like they're being hit by a sledgehammer from the inside.
Yeah, it's a very distinct, alarming sound.
It's startling.
Yeah.
And the sources mention that the new equipment volume updated the safety factors for something called a steam trap to prevent this.
Yeah.
What exactly is the fluid dynamics happening there?
Okay, so it is a violently destructive force.
Violently.
Oh, yeah. In massive facilities like power plants, university campuses, large hospitals, they distribute heat using high-pressure steam.
Right.
Steam is incredibly efficient for moving thermal energy over long distances. But as that steam travels through the piping network and radiates heat into the building, it naturally cools.
And condenses.
Exactly. It condenses back into liquid water, which engineers call condensate. So you have a pipe carrying high-velocity gas, but there is a layer of liquid water starting to pool at the bottom of the pipe.
Right. And here is where the physics get dangerous.
Okay.
That high-speed steam can catch a wave of that liquid condensate, pick it up, and accelerate a solid slug of water through the pipe at highway speeds.
Oh, wow. And water doesn't compress.
It does not compress at all.
Right.
So when that high-velocity slug of water hits a valve, a sharp bend in the pipe, or a sensitive piece of machinery, it transfers all of that kinetic energy instantly.
Like a car crash.
That is exactly what a water hammer is. It can blow out welded joints, destroy expensive control valves, and it is a severe safety hazard to anyone standing nearby.
So how does a steam trap solve a high-speed liquid battering ram?
A steam trap is essentially a mechanical valve designed to differentiate between gas and liquid.
Okay.
It selectively allows the liquid condensate to drain out of the high-pressure pipe while trapping the steam inside so it can keep doing its job. What the committee did in the 2024 equipment volume was update the mathematical safety factors for sizing these traps.
And there goes the chain reaction again.
See it now.
Because the mathematical sizing of that one component changed, the engineers working out of the applications volume have to completely recalculate their steam distribution networks for industrial power plants.
Yes.
They have to change pipe slopes, trap spacing, and return lines, all to ensure that this destructive hydrodynamic force is neutralized before it can ever form.
It just goes to prove that the handbook isn't just theory.
Yeah, it's very real.
It is a continuous living dialogue between the fundamental laws of fluid dynamics and the real-world need to keep a hospital warm without exploding a pipe in the basement.
Okay, let's zoom in entirely on that real-world application. Let's look inside the 2023 HVAC Applications volume.
Okay.
Because this is the exact text an engineer has open on their desk when they are designing the spaces we actually live and work in today.
It is a staggering document, really.
Huge.
The 2023 edition has 67 highly specialized chapters. It is essentially a comprehensive index of human activity.
What kind of chapters are we talking about?
Justice facilities, aircraft, indoor swimming pools, underground mines, museums.
Mines. Wow.
Yeah. If a human occupies a space, there's a chapter defining the exact thermal and atmospheric parameters required to keep them functional in that space.
And what's fascinating is seeing where they felt the need to add entirely new chapters.
The additions are very telling.
The sources highlight 2 brand new additions for 2023, and they really telegraph where society's anxieties are right now.
Absolutely.
The first new chapter is fire and EMT stations and training academies. My first thought was, isn't a fire station just a big garage attached to a bunkhouse? Why does it need a completely bespoke engineering chapter?
That is a very common misconception, but a modern fire station is actually one of the most complex hybrid environments you can build.
Really? Why is that?
Well, you are dealing with massive diesel engines starting up indoors,
Right, the trucks.
which introduces acute toxic exhaust loads that have to be mitigated instantly without sucking all the conditioned air out of the building.
Right, you can't just open a window if it's freezing outside in winter, but you have to get the diesel fumes out before they migrate into the living quarters.
Exactly. You need aggressive pressure mapping to keep the living areas at a positive pressure relative to the apparatus bay, so fumes physically cannot enter.
Oh, so the air is always pushing away from the bedrooms?
Yes. Furthermore, you have the physiological needs of the responders. These are personnel returning from extreme thermal and physical stress.
They need to recover quickly.
They need highly specific environmental conditioning to recover. Plus, you have turnout gear drying rooms.
What are those?
Spaces strictly designed to rapidly pull moisture and off-gassing carcinogens out of their heavy protective equipment. A standard commercial office HVAC design would fundamentally fail in a fire station.
That makes total sense. You are managing biological stress and toxic chemistry in the exact same footprint.
Yes, it's incredibly demanding.
The second new chapter they added is in-room air cleaners, which directly addresses removing pathogens from occupied spaces. Again, you see global events directly forcing the engineering consensus to adapt.
The handbook is an uncompromising mirror of technological and societal leaps.
Yeah, that's a good way to put it.
And nowhere is that more evident than in Chapter 20, which covers data centers.
Let's talk about that because the AI boom has completely upended server technology.
It has rewritten the rules.
Our sources note that this chapter was heavily updated to align with modern IT demands, specifically the inclusion of direct-to-chip and immersion liquid cooling. It seems like the era of just blowing cold air down an aisle of servers is totally over.
It basically has to be over because the physics of the new processors demand it.
They run too hot.
Way too hot. The heat flux, which is the amount of heat generated per square centimeter of a modern AI processor, has surpassed the capacity of air to remove it. Air is actually a terrible conductor of heat.
So they have to fundamentally change the cooling medium.
Yes. They are now actively engineering systems where specialized dielectric fluids are pumped directly to cold plates on the chips.
Wow.
Or, in extreme cases, the entire server rack is submerged in a bath of engineered fluid that undergoes a phase change.
Like it boils.
Exactly, boiling off and condensing to carry the massive amounts of heat away.
Which introduces an entirely new problem: water consumption.
Oh, yes. A massive issue.
The sources highlight that the new standards focus heavily on water concern management because these massive AI data centers are pulling millions of gallons of water from local municipalities just to reject that heat into the atmosphere.
It is a critical resource collision.
For sure.
The digital infrastructure requires immense cooling, but physical water scarcity is a growing global crisis.
Right, you can't just drain a town's water supply for ChatGPT.
So the engineering standards have to provide rigorous strategies for maximizing cooling efficiency while drastically reducing the evaporative water loss.
It is fascinating how quickly an invisible digital technology like cloud computing and AI forces a massive physical engineering problem regarding local water tables.
It's all tied together.
That same kind of societal shift is evident in Chapter 36, which covers solar energy use.
Yeah.
It is no longer just about slapping photovoltaic panels on a roof, right?
Not anymore, no.
The sources say they expanded it to include green hydrogen as a local energy storage and thermal power generation source.
This represents the most significant philosophical shift in building design right now.
How so?
We are moving away from the idea of a building as just a passive consumer of fossil fuels,
Okay.
and moving toward the building acting as a dynamic, decarbonized participant in a larger microgrid.
Ah, so it produces its own power.
Generating power, storing it chemically as green hydrogen, and utilizing it for thermal heating when the sun isn't shining.
I want to pivot to a specific engineering problem that really caught my eye in the sources.
Okay, let's hear it.
Chapter 4 covers tall buildings, and they expanded the discussion and added new math examples for something called the neutral pressure level, or NPL.
Oh, the stack effect, yes.
Right. I have to ask about the physics here, because I used to work in Chicago.
Probably the perfect city for this.
Yeah. And in January, walking into a high-rise lobby was, it was an extreme sport.
They're fighting the building.
Yeah, exactly. You'd pull on the heavy glass revolving door, and it felt like fighting a wind tunnel just to get into the building. Is that what this chapter is trying to solve?
That wind tunnel you fought in Chicago is the exact reason Chapter 4 exists.
Mm-hmm.
You were experiencing the stack effect.
The stack effect. Okay.
When you build a structure that tall, it stops acting like a conventional building and starts acting like a massive vertical chimney.
A chimney. How so?
Well, think about the thermodynamics in the dead of winter. It is freezing outside. But to keep the occupants alive, you are pumping massive amounts of heat into the interior of the skyscraper.
Right.
Warm air is significantly less dense than cold air. It has buoyancy. So naturally, that vast volume of heated air wants to rise.
Right, hot air rises.
But in a skyscraper, it has massive, uninterrupted vertical pathways to travel through.
Like the elevator shafts.
The elevator shafts, the emergency stairwells, the central atriums.
Oh, man.
As thousands of cubic feet of warm air rush up these shafts and push against the upper floors, it creates a powerful, low-pressure void at the bottom of the building.
Like a vacuum trying to fill itself?
Exactly. That massive low-pressure zone at ground level forcefully sucks in the dense, freezing outdoor air through every tiny crack and, most noticeably, through the main lobby doors.
So what is the neutral pressure level, then, the NPL?
The NPL is the specific vertical elevation in that skyscraper where the interior pressure exactly matches the exterior atmospheric pressure.
Okay.
Below that invisible line, the building is sucking air in. Above that line, the building is violently trying to push air out.
So why does an engineer need complex mathematical models to figure out exactly where that invisible line sits? What happens if they just ignore it?
Oh, if you don't calculate the NPL and aggressively manage it with mechanical design, usually by creating isolated pressure zones or mechanical airlocks throughout the building, the physics take over with disastrous results.
Like what?
The pressure differentials become so extreme that human beings physically lack the strength to push the lobby doors open against the vacuum. They become sealed shut.
Wait, really? That's terrifying in an emergency.
It is a massive life safety issue, but it also destroys the internal mechanics.
How does it do that?
The lateral pressure on the elevator shafts can become so immense that the elevator doors cannot close. Or worse, the pressure physically bends the steel guide tracks, trapping the cars.
Bends the steel tracks.
Yes, and the acoustic whistling of air forcing its way through the structural seams becomes deafening. Managing the stack effect is the only way a skyscraper can remain functional.
That is absolutely mind-blowing. The building is essentially a giant thermodynamic machine that is actively trying to rip its own doors off and jam its own elevators.
Pretty much.
And the only thing holding it together is an engineer applying the math from the ASHRE Handbook.
That is the core reality of the profession.
Yeah.
Translating the immutable laws of physics, like the density of warm air, into practical, code-enforceable design strategies that tame those forces and keep us safe.
So, okay, let's unpack this and synthesize everything we've looked at today.
Sure.
The ASHRE Handbook is fundamentally not a dusty set of encyclopedias sitting on a shelf.
Not at all.
It is a highly active, living consensus. It eyes this invisible operating system that draws a direct mathematical line from the microscopic behavior of a pathogen or the exact flammability of a new chemical coolant, all the way to the structural integrity of a megatall skyscraper.
It represents the accumulated, hard-won, ground truth knowledge of tens of thousands of practitioners.
Yeah.
It is constantly being debated, rigorously peer-reviewed, and updated to reflect the reality we live in.
So the next time you walk into a crowded venue and don't immediately feel suffocated, or you stand in an archive and the humidity is flawlessly controlled to protect a delicate artifact, or you just don't hear a high-speed wave of water hammer destroy the plumbing in your office building, remember what's actually happening. You are experiencing the direct, localized result of this massive global effort.
You really are.
You are standing inside the physical application of the handbook.
It is the triumph of collaborative engineering. A safe built environment isn't an accident. It is a meticulously documented science.
Which brings us to one final, deeply provocative thought based on the sources.
Oh yes, the AI policy.
Right. Looking at the very beginning of the historical overview, ASHRAE has instituted a strict AI policy. They explicitly prohibit their intellectual property, these carefully crafted human-debated volumes, from being entered into AI tools like ChatGPT to create derivative works.
They are fiercely protecting this human-generated consensus.
Which is understandable given the liability and the need for verified expertise.
Absolutely. The legal stakes are too high.
But as we saw in the updates regarding smart building systems and those liquid-cooled AI data centers, the infrastructure itself is accelerating rapidly.
Very rapidly.
So here is the question we are left with. What happens when the physical design of buildings becomes fully automated?
It's a huge question.
As artificial intelligence becomes sophisticated enough to run complex thermodynamic simulations natively, will the future ASHRAE handbook even be read by human engineers?
Or we'll just bypass humans entirely.
Right. Will it inevitably become a protected, encrypted dataset fed directly into a generative AI system that simply spits out perfectly balanced, thermodynamically flawless, code-compliant building blueprints in a matter of milliseconds?
That points to a massive impending shift in the discipline.
Yeah.
If the invisible operating system eventually designs the invisible operating system, who is left to ensure the machine isn't hallucinating a catastrophic mathematical error?
Exactly. When the math is being done by a black box, we might just have to trust the simulation. Something to think about the next time you step into a skyscraper and brace yourself against those lobby doors.